name's Nicolson, and for this video, I'm going to be applying the Nicolson method to the finite differencing equation and hopefully proving that for any value of r, it produces stable results. Previously, we had looked at just looking at the finite differencing equation, and we found that we ran into an instability when r was greater than 0.5. So hopefully, by applying the Nicolson method, we can reproduce an equation that is solvable for any value of r and does not produce exponentially growing errors. So, starting off with the heat diffusion equation for just one dimension, just the x-plane, and we're going to be applying similar method to what we did in the previous video, where we're going to be expanding this change in temperature over your change in position, change in temperature over your change in time. And I'm going to be using the same notation previously, where J corresponds to position and N corresponds to time. So your temperature at the position of interest, or the block of interest, one time period in the future is going to be equal to, minus your temperature of the block of interest at the current time period divided by your change in time. This is basically taking the average of that to get the derivative, and that's going to be equal to your heat diffusivity. And then again, if you remember from the previous video, we expanded this to take an average of the temperature over 2, basically the position squared, and I'll pull that again just to start with. So we have your position, or the temperature of the block in front, so Tj plus 1 at the current time, minus 2 times the temperature of the block of interest, plus the temperature of the block 1 in front to the left at the current time, all over change in position squared. And if you don't remember how we got this, check out the previous video, I think it's 2 videos prior, where we actually derived it. And Nicolson method basically states that we take it over a larger period of time and we take an average of that in order to get a more accurate finite differencing equation. So we're going to be going one time step in the future of this whole term. So it's going to be, again, the temperature of the block 1 in front, one time step in front, minus 2 times the block of interest, one time period in the future, plus the temperature of the block to the left, one time step in the future, and again, all over your position squared. Cool. And in order to take an average of these two, I'm going to throw around a parentheses around this, and it's going to be final minus initial. So this is your final term here, and this is your initial term here. So throwing in the negative there, and then in order to take the average of the two, I'm going to divide it by 1/2. Okay, and in this equation, r is a little bit different than just previously with the finite differencing. And this time, I'm gonna actually, and for this run, I'm actually gonna call r as equal to your heat of diffusivity over 2, move over your change in time, your time step. So change in time over change in position squared. So we actually have that dividing by 1/2, and it looks a little bit different. So I'm gonna simplify this as r. I'm gonna rewrite this equation again, simplifying it a little bit more. And we have your temperature at position J, one time step in the future, minus the temperature, actually I'm gonna move this over, is equal to the temperature position of interest at the current time, minus, plus r, big parentheses, and encompassing these 3 terms and these 3 terms. So the temperature at 1 in front, one time step ahead, minus the temperature of the block of interest, one time period in front, plus the temperature of the block to the left, one time period in front. And then again, it's going to be all subtracted by your temperature one block in front at the current time minus 2 times temperature block of interest at the current time plus temperature of the block to the left at the current time. And the reason you can't actually condense any of these terms further down is because they're at different time periods. So this is one time period in the future, and we're calling this the current time period n. So what can we do from here? Well, we can actually shift all the terms that are in the future over to the left-hand side of the equation and actually work to simplify this a little bit more. So I'm going to take a couple algebraic steps to simplify this down. So moving these 3 terms over, I'm going to get negative r times your temperature of the block to the right, one time step in front, plus 1 plus 2r times your temperature of the block of interest, one period in front. And basically, these 2 terms here, I factored out the temperature of the block of interest, one time step in front, to get this 1, and again, it's multiplied by r, so that's where that 2r comes from. And then again, a negative r times your temperature position to the left, temperature of the block to the left of the block of interest, times that, or to the, I'm going to say that again. It's going to be negative r times the temperature of your block to the left of the block of interest, one time step in the future. It's a lot, sort of tripping over my words. And then it's going to actually work out nicely. You're going to get a little bit of symmetry. It's going to be very similar to what is over here, but it's just going to be r. It's all just going to be in the same time period. So r times temperature of the block 1 in front at the current time, plus 1 minus 2r temperature of the block of interest at the current time, plus r times the temperature of the block 1 to the left at the current time. And let me actually circle this. So this is what we have here, and it's extremely ugly. And in order to solve it, actually, we need to apply some matrices applications. And specifically, we're going to be using a tridiagonal matrix. Actually, let me write that out so you don't forget it. Tridiagonal matrix. Try saying that fast 3 times. Tridiagonal matrix, and which can actually be solvable by the Thomas algorithm. I'm also going to write that out in case you want to do some Googling. So that can be solvable by the Thomas algorithm, but just so you can sort of further understand what's going on here, I'm going to break it up into matrices and sort of analyze it to make sure it makes sense with what we're actually, our physical setup is. Cool. I'm gonna do this in a different color. It's a lot of blue. Let me write, okay, so let me write this. Cool. So basically we're gonna have 3 sets of arrays when we go into, so spoiler alert, we're gonna jump into Google Colab and actually code something, a couple lines of code and use some neat packages to actually solve this. So we're gonna end up with 3 arrays. 2 of those are gonna be multi-dimensional, and this is gonna be your unknown so this is your temperature at position 1, temperature at position 2, and it's going to go all the way down to tj of n, or n minus 1, depending on how you denotate what the end of the block is. So these are our unknowns, and on the right hand side we actually know the temperature at the current time for that block, So these are knowns, and they're going to be R, that's your temperature. So for the first iteration, J is equal to 1, so it's going to be R times your temperature at block 2 plus 1 minus 2R temperature of the current block of interest plus R times your temperature of the block to the left. And so I'm actually going to point out some special blocks, and those will be your T at position 0 and at position N. And I'm going to be using Python syntax to reference the blocks, calling them an array basically. So this is going to be position 0, and if you remember the setup, this is always going to be at 350 degrees Kelvin. So that's a constant temperature. That's not actually going to change with time. So keep that in mind when we go over to solve this tri-diagonal matrix. And the other end of the block, position N, yeah, we're going to call it N. Well, in Python, I'm going to call it N. In Python, it's going to be referenced as N minus 1. And that has temperatures of 400K. And also a quick reminder, N being the number of divisions you have dividing this line by. So those two N's are always constant, and we always know those. So for this instance, that's what it would be. And especially since the initial condition, we always know what the initial temperatures are. Just to refresh, everything inside is 300 degrees Kelvin. I'm gonna go ahead and write out another line just so you can sort of get a feel for the pattern. So it's gonna be R times your temperature at block 3 plus 1 minus 2R temperature at block 2 plus R times your temperature at block 1. And this pattern will continue for however many blocks you decide, and n number terms. So this is what we actually know, and this is what's known. These are our unknowns, which is basically your time one step in the future. I'm not going to denotate that. And then over here, we can solve these three terms to actually create a tri-diagonal matrix. I'm saying that word a lot. Probably like, what the heck does that even look like? Well, it's sort of what it exactly sounds like. And so for the first term, we're going to say J is equal to 1. And over here, no. This is, okay, so this is the block to the left. And if you remember, at J is equal to 1, that's going to be your temperature at block 0. And we actually know what the temperature at that block 0 is. So it's not going to be included in this matrix. But it's still relevant. It's still very relevant. And we need to go over and throw it on our known side. So this is going to be R times T0. Because it doesn't matter what time period you're at. So n plus 1, n plus however many you want. This block at 0 is always going to be 350 degrees Kelvin. And it's always going to be the same for the other end of the block here too. So I'll go ahead and throw in a T plus RTN, because that's known for any time period. And it's not going to change as time progresses. So that leaves us with two terms that are non-zero in this array. This array will have length of the number of terms that we have. So I'll just write that. Length equal to n. So it's going to be a lot longer than what I actually drew out here, but I just condensed it down for space. So J is equal to 1. Looking at this, it's going to be 1 plus 2R TJ1. Actually, no, there's not going to be any TJ because we pulled out the unknowns, which is one time step in the future over here on the right. And then the next spot in the matrix is going to be the right-hand block, which actually will exist, and that's going to be negative R. And then the rest of these are just going to be zeros going for the rest of the matrix, for the length of the matrix, which is the number of divisions and number of blocks you have. Then going down to j is equal to 2. We do actually have an unknown here, so j is equal to 2 minus 1. That's going to be j of 1 time step in the future. So that's where we're going to have our term here, and then j is equal to 2, plugging that in there. The second term in this matrix is going to be 2, or this line is going to be 1 plus 2r. The third term is going to be j is equal to 2 plus 1, so it's again going to be negative r. And then let me actually just do a dot 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 there. Dot 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 dot. That's going to be 0 all the way down. And I'll solve it one step further so you can sort of see the pattern and what evolves. J is equal to 3. We don't have any terms for that j is equal. Actually, we don't have any terms for that j is equal to 1 block, but we do have something for that j equal to 2. If we solve it here, it's going to be negative r. Plugging in j here, you get j. 1 plus 2r, and then j is equal to 3 plus 1, so that's going to be equal to 4, negative r. And let me actually denotate something along here to actually help and emphasize how this pattern continues. And so this is going to be j is equal to 1, j is equal to 2, j is equal to 3, and so on and so on. So each row corresponds to a position of a block 1 time step in the future. Let me write that out so you can separate. Yeah, so basically it's going to continue forward where you're going to have these 3 terms. So that's where the tri-diagonal is going to be going diagonal matrices, and the rest of the terms are going to be 0 in this. And in order to actually solve this and see how it progresses with time, we're going to need to code it, because there's no way I could ever do this by hand. It's not enough money on the planet to make me, or to motivate me to do this. But I'm actually going to go jump over to Google Colab and code something out and see what it looks like. And hopefully we will end up being able to prove that for any value of r, we can produce an unconditionally stable equation as time progresses. So cool, gonna jump over to Google Colab. Okay, jumping over into Google Colab, I'm going to code out and graph the finite differencing equation, which we derived earlier in the video using the Nicolson method. First, it's going to be very similar to the previous video, where we're going to use NumPy and Plotly to actually graph. Yeah, so we're going to want to have something that we can actually plot on using Plotly subplots, and then also we need to have something for our tri-diagonal matrix in order to solve that, and we're going to actually going to use SciPy and import a function called solveBanded. I have it open in the other tab, and you can do a Google search if you're interested in reading into some of the arguments it takes. But basically, the 3 main components are you input the lower and upper number of rows. So in our case, we have a tri-diagonal matrix. So we're going to have 1 lower row, 1 upper row. And then we're going to have our banded matrix, which is basically we'll take our diagonal matrix and make it horizontal. So in this case, we'll have 3 rows with length of number of divisions -2, because we know the set positions at the end. And then also we're going to have our temperature profile, which will be B, and that is what we're going to actually update. Cool. That's the right-hand side of the equation, which we derived and we solved earlier. So starting with, I'm going to define how many divisions we'll have in the bar. We'll do 100. Number of timestamps, we'll do 1,000. And then from there, also want to go ahead and establish that R value. We're going to go ahead and jump straight to 1. I know we reached the limitation at 0.5 last time we derived the finite differencing method, but today our goal is to prove that we can use any R value
and it won't cause any instabilities or increasing exponential error. Cool. Okay, from there, I'm going to actually create an x-axis, similar to what we did. X-axis is going to be 0 to how many number of divisions we have. I'm also going to create our temperature profile, full NX, and everything's going to be initially at 300 degrees Kelvin. We're going to have the number of divisions we have. And then we know our initial conditions of the left-hand side of the bar being at 350 degrees Kelvin. I don't know why that popped up. And then the right-hand side of the bar being at 400 degrees Kelvin. Remember, you're going to use array syntax, and we're going to reference the other end by using a negative number. Next, we also need to declare our banded matrix. So we're going to do A is equal to NP. I'm trying to think of how I want to do this. Let's do empty. Yeah, let's do empty. Empty, and it's going to have 3 rows, each having the length of total number of divisions minus 2 because we're excluding the ends, and then I actually want to go ahead and define each individual row. And so this will assign values to the entire row. For the first row, it's going to be negative r. For the second row, it's going to be 1 plus 2r, which we derived in the equation earlier, and I sort of mapped out the matrix. And again, this is our banded matrix, this was our tridiagonal matrix, and we're turning it into a banded matrix. So next, in the last row, again, following symmetry is just going to be negative r. Cool. And then from there, we also want to go ahead and create that function which we're going to update with the values. We'll do empty, and this is going to have the length of the bar minus 2 because we're not going to include the ends. Okay, and then we want to go ahead and actually establish the initial temperature profile position by writing out what the right-hand side of the equation was. So if you don't remember, you can reference it earlier in the video, but basically we're going to have the first term is going to be referencing the block rightmost to the block of interest, and then it's going to go all the way to the end. We don't want to include the very ends. Using vector matrix, it's the ends. The right-hand side is not going to be inclusive. So from there, we're also going to do the same thing for the left-hand side, which will go from the beginning to the end, almost the end. I'm going to run this, hopefully get no errors. Cool. There's one last piece of the puzzle, and we actually need to go ahead and tack on the initial conditions to the end, both ends of the bar. If you remember the tridiagonal matrix, there was one term at the beginning and one term at the end, which it didn't encompass, and that was because for any value of time going to infinity, we know that the left-hand side of the bar and the right-hand side of the bar are going to be at the constant temperatures of 350 degrees and 400 degrees. So how we'll actually go ahead and apply that is we'll take the value of what it normally is and then do r times the temperature of the initial. And then again, we need to do it for the left-hand side, or the right-hand side, sorry. And if you are following along, you know that these matrices, or these arrays, are not the same length. So even though we call this the first term in row B, that actually is too short of the number of divisions we have. So it's actually going to be the first block, whereas T of 0, that is actually referencing the true first block in our band, called the band. Next, also want to create a subplot. Make subplots. I always create it as plural. Rows 1, columns 1, and then we're going to actually go ahead and add our initial condition. Again, we have our x-axis. We defined that earlier. Our y is going to be equal to, our y-axis is going to be equal to our t values, our temperature values, our mode. We're going to have lines, because we actually want to connect all the scatter plots. And then for the name, we'll call this something very generic and inspirational, like initial. So hopefully runs. Everything's good there. I think it might show up the initial plot. Yeah, okay. So it's going to show our initial condition, and here we see we have 350 degrees on the left-hand side and 400 degrees on the right-hand side. And the rest of the bar is at initial position or temperature of 300 degrees. So next, we're going to want to go ahead and create our iterations and our for loop. Actually use one. And in that for loop, we're going to actually solve the banded equation just for the ends. We're not going to update the... So we're going to actually solve our banded equation for the middle values, not including the ends. And remember, the first argument is the number of rows. Let's see if it pops up. Yep, L and U. We have one lower row and one upper U or row in the banded matrix. We have A as our banded matrix, B as the value of the right-hand side of the equation, which is what we're going to be updating. Another part is with each iteration, we're going to need to update that value of B for it to actually affect how it's solved with C or T, the temperature array. So it's going to be the exact same as what we typed out before. And then again, for just visualization purposes, I'm going to use the modulo operation to graph some lines. And we'll add scatter. Excuse me. Again, X is the x-axis, y-axis is going to be our t values, temperature values, and mode is going to be lines. We want to connect the dots, and for the name, we're going to want to reference this as whatever value it is. Show, and we'll want to actually show it at the end of each iteration. Okay, so for I in range, a little rusty with my Python. Okay, didn't like that either. Let's see what happened. Solve banded. What error are we getting? Array must not contain. So taking a look, let's take a look at the beginning and actually run through everything, just so you could sort of see how I would actually troubleshoot this, as if it were my first time doing it. We're writing up our divisions in the bar. We're having our time, number of time steps we want to step through. We have our R values declared, our axes, temperature, initial condition. We're going to call it full of those values. We got a 3D array, which 3 rows. Yeah, 3 rows, number of columns being each temperature value. It's going to be we're going to define each row of the banded matrix, plotting it from a tridiagonal matrix. Initially, we want to have an empty array. This should define it for every value. Maybe, I don't think we're going to update the ends. What's the issue? Let me go ahead and actually run that. Maybe we do need to include the ends in our matrix which we're solving. Pretty sure we don't. No. So that first value, we're getting an issue with this temperature profile. Did I call everything correctly? Yeah. We have our banded matrix. Let me just double check. Yeah. A is our banded matrix. Solve banded for range NT. I feel like it's something glaringly obvious that I always forget. I think we're gonna. Oh, it's gonna be a minus. Yeah. So that's gonna be minus 2r. I had our equation wrong. I don't know if that'd give us the error we got. So we'll actually see. It's looking a lot better so far. Oh, wow. Yeah, that actually was the error. So here you can see that for an R value of 1, we don't get the irregularities and then growing errors of what we previously saw. Here, we almost approach a steady state. I'll take it out a little bit farther, just so we can sort of see. Actually, no, I'll keep it the same number of time steps. I'll just double R and show you that for another value of R greater than 0.5, it is a stable solution. And there you have it. Yeah, it reaches steady state, probably around like almost the 900th iteration. And we can decrease the time further and make R a lot larger. So let me go ahead and just do an R value of 5. And I haven't done this before, so the results will be a shock to me too. But let's go ahead and make sure we update each code block, updating our values. And then, yeah, okay. So this is another thing I sort of wanted to point out, is that initially if you have too large of an R value, it will take too big of a step at that first iteration. But as you can see, it learned how to it corrected itself, and the errors weren't growing exponentially like we previously saw. So that's it for this video, deriving the finite differencing equation again, but this time using the Crank-Nicolson method, and we can actually produce some stable results. Thank you for watching. Hopefully it was helpful,